Swayam Prabha. Digital India. Educated India.
Hello everyone, hope all of you are doing well. In today's class, we will conclude our discussion on energy bands, and we will try to understand the notion of effective mass. And before going into that discussion, let me quickly summarize what we discussed in the last class. In the last discussion, we saw that the KP model solution gives a constraint which naturally tells us that there are certain energy values in a solid which are disallowed for the electron to take, and there is a certain energy range which the electron can take in a solid. Okay, and this is the graphical representation of the constraint, the function that is there in the solution of the KP model, and this is the intuitive picture of allowed and disallowed energy values of electrons in a solid. This is the crystal momentum, these are the edges of the crystal, these are atomic cores here. So, that is why the potential energy of the electron is going to negative infinity at these points, and these shaded regions, these are the allowed energy values that the electron can take in the solid. Okay. So, now extending this discussion, if we plot the E values, the electronic energy values and the K values, this is what we get basically. This is the plot that we obtain. And as we discussed in the last class, there are certain conditions that naturally come from the solution of the Bloch's theorem, which we can see from its derivation, but which we can also see from the statement of the Bloch's theorem. And one of those conditions is that all K values can be all K values lie in a range of 0 to 2 pi by period of the potential profile, or from minus pi by A, capital A, to plus pi by capital A, where capital A is the period of the potential profile. In our solution, the period of the potential profile is capital A is small a plus small b. So, all possible K values will be between minus pi by A plus B to plus pi by A plus B, and corresponding to these K values we will have many energy values basically. The solution also the solution of the Schrodinger equation and Bloch's theorem, statement of the Bloch's theorem also conveyed that there will be an energy range for which no K value will exist, and this we can see from here. So, these energy ranges, this y axis is the energy axis, x axis is the K axis, these highlighted portions on the energy axis, these are the energy range, these are the energy values which do not have valid wave function of electrons, which means the electrons cannot take these energy values in the solids, or there is no K value corresponding to these E values, and these are also known as the band gaps, because this is a gap in the energy axis, this is the gap where no electron can exist on the energy axis. Okay. Also one of the conditions that we also studied, that if we shift the k value by 2 pi by the period of the potential profile, the wave function remains the same. Basically, the wave function does not change, it corresponds to essentially the same wave function. Okay. So, this is this will sort of tell us, by making use of this condition, we will see that there is an alternative way of representing or alternative way of visualizing the EK relationship for a 1D solid, and which is essentially can be given by this. So, what we can do is we can now shift this plot by 2 pi by a plus b in either direction, left or right. So, that is what we do, and if we shift this to the left by 2 pi by a and this to the right by 2 pi by a, this to the right, this to the left by 2 pi by a, okay, and this to the left, this to the right by 4 pi by a, 4 pi by a, here it is 4 pi by a plus b. This is what we obtain. Here y axis is the energy axis and x axis is the k axis, and on this EK axis system, this is the allowed values of energies as a function of k. And as is also clear from this plot, certain energy values, for example, this range of energy values, these are the disallowed energy values or the band gaps of the solid. Okay. So, this is so to say, this is the first band, this is the second band, this is the first band gap, the band gap between band number 1 and band number 2, this is third band, this is fourth band, which we can easily visualize here. Okay. Along with this, there is a plot of EK relationship for a free particle as well. If you recall from one of our previous discussions, for a free particle E is related to k as h bar square k square divided by 2m. So, it is a parabolic relationship which we can also see here. Okay. So, we have the EK relationship for a free particle, free electron, so to say, electron which is free from all the interactions, and we have EK relationship for an electron in a 1D solid. As you can see, for higher energy values, for when the energies are quite high, the EK relationship for the electron in the solid and the EK relationship for the free electron, they approach to each other, basically they converge. So, what it means is that if an electron has extremely has high energy, is extremely high energy, it has, then it is quite like a free particle, free electron. Okay. But the EK relationship for electrons in solid, in a 1D solid and a free electron is quite different for low energy values, for the low energy electrons, when the electronic energy is not so high. What it means is, low energy electron means that the electron is confined in the solid, electron is tightly confined, or not, I would not say tightly because that word has been used in a different context. Electron is does not have too much of energy to sort of move away from atomic cores, but it is still moving in the solid. It is not like a free electron, but it is moving inside the solid, and for low energy values, the EK relationship between EK relationship for a 1D solid and for free electrons are very different, as we can see here. So, this is one observation, and with this we also comes the notion of the Brillouin zone. So, Brillouin is not the precise pronunciation of this word, this is a French name, but still for the sake of better sort of understanding, I will use the Brillouin pronunciation. Brillouin zone is a set of k values corresponding to an energy band. So, the set of k values which correspond to first energy band, they are known as Brillouin zone 1. Similarly, corresponding to energy band 2, they are Brillouin zone 2. Similarly, corresponding to third band, they are Brillouin zone 3. This is how this is defined, and this is very important concept in solid state physics. And generally, whenever we analyze a new material whose property we do not know beforehand, we first try to find out the relationship between E and K for that material. So, that tells us a lot about how electrons will behave in that new material. So, this notion of EK relationship, notion of Brillouin zone, it is quite important for understanding the nature of electrons in solids. There is one more point here. For an electron in a solid, although we did not do it mathematically, a precise analytical solution we did not do here. Most of after a stage we are using a graphical solution for the sake of better understanding, but at the boundaries of Brillouin zones, del E by del K is 0. What it means is that at these points, these boundary points, del E by del K, the gradient of EK plot is 0. Okay. Also at this point. So, this notion, this idea will be useful for us in the next discussion, which is the discussion on effective mass. So, this is essentially the broad idea of energy bands in a solid, how the energy bands arise in a solid, and that is a consequence of periodic potential in solids. And using KP model, we can see that, we can visualize that mathematically as well as graphically. Okay. So, but we at the outset, in the beginning, our aim was to understand how the electrons will behave, and what I mean by behave is how the electrons will be transported in a device, or the transport behavior of electrons in a device. And we started with a simple 2-terminal device like this, where we have 2 contacts, source and drain contacts. In between we have a channel region, and we saw that the channel region is becoming smaller and smaller in modern devices. Generally, we apply a positive voltage on the drain terminal, which makes electrons flow from source to drain, or a current from drain to source. So, this needs, in this we need to know how electrons are travelling, we need to know about the motion of the electrons. So far, our discussion has been primarily focused on what is the allowed energy value that the electron can take in a solid or in a particular environment, and what are the K values that electrons can take in a solid or in a particle in a box situation or as a free particle. So, our discussion so far has been focused on the allowed energy values or the K values. So, in that sense, we have solved the Schrodinger equation where the energy and momentum are precisely defined. So, energy of the electron is precisely defined and the momentum of the electron is also precisely defined, but that is not sufficient for understanding the motion of electrons in actual solid. So, we cannot understand the motion of electrons in solid using this, and the reason for that is that quantum mechanics has another principle which is a consequence of the measurement of quantum mechanics. That this principle is known as Heisenberg's uncertainty principle, and what it says is that there is a set of complementary variables. There are many complementary variables in quantum mechanics which cannot be measured simultaneously, and these variables are known as complementary variables or conjugate variables. So, so energy and time is one such pair. If we know about the energy of an electron precisely, we cannot say about its sort of motion, about its dynamics. If we know the position or if we know the momentum of the electron precisely, we cannot tell about the position, exact location of the electron, and this is known as the Heisenberg's uncertainty principle, and this is the mathematical inequality that captures the Heisenberg's uncertainty principle. What it says is that the uncertainty in energy and uncertainty in time to which we can precisely measure an electron is always greater than or equal to h bar, and similarly the product of uncertainty of momentum and momentum and position is greater than or equal to h bar. So, what it means is that if we precisely try to measure the momentum, the uncertainty in position will be high, and similarly if we try to precisely find out at a certain time where the electron is, how it is behaving, what is its wave function, its energy will not be well defined. But in our discussion up to this point, we have sort of precisely defined the energy and precisely defined the momentum of the electron, which is momentum of the electron is related to the this k parameter, the wave number parameter basically. So, based on the discussion that we have done so far, we cannot sort of visualize, we cannot understand the motion of electrons in actual solids. Although building on this, this is the building block, this the discussions that we have done so far is the building block of our understanding of electrons, and in this context this notion of effective mass basically arises. So, we will see that what it is, we will see what it is. For a single wave function, as we have seen, the energy and momentum is precisely defined, but if we have an electron, for example, if we in this device an electron is starting from the source going through channel up to drain, we have an idea or we have basically determined the path of the electron. We have electron which is confined in certain dimension of the space, which is confined between source and drain. So, if the electron is in channel, it is confined in a certain length. So, what it means is that now there is some clarity about the position of the electron. So, in that sense the momentum of the electron cannot be precisely defined, there will be uncertainty in the momentum, uncertainty in the k values as well. Similarly, if we want to understand what is the position of electron at a certain time, at a precisely at a certain instant, its energy cannot be precisely defined. So, that is why generally in all practical devices, in all sort of for all practical purposes where the electron is, we know that electron exists in this regime of space, in this, for example, in channel, in this region of space. In that case a single wave function cannot describe the electron, because a single wave function has precisely defined energy and k values, And now the energy and k values, energy and momentum values are not precisely defined, because some clarity is there about the position and the time. Okay. So, that is why in all practical devices, in most of the practical devices, the electrons are characterized by a bunch of wave functions. Electrons will have wave functions corresponding to different energy values, so that the energy uncertainty will be there, and this bunch of wave functions is known as the wave packet. This term appears in classical wave mechanics as well. So, in practical devices, when we have some clarity about the position of the electron, generally the electron will be characterized by electrons will be defined by a collection of wave functions or by a wave packet. So, a wave packet is essentially collection of wave functions corresponding to different energy or k values. So, I hope this point is clear, that in an actual device where we have clarity about the position and timing of the electron, that at this time the electron is moving from this to that, although we might not know where that is precisely located, the electron is precisely located, but in that case energy and momentum will not be precisely defined. So, we cannot define electron by a single wave function, and that is why the electron will be defined by a collection of wave function or wave packets. Now, we have wave packets of different energies, different momentums, and that will make sort of a bunch of waves, and that bunch of waves or wave packet will move with certain velocity, that is known as the velocity of the wave packet. And from the classical mechanics dispersion relationship, the velocity of the wave packet is given by the dispersion relation Vg, the group velocity of the wave packet is given by d omega by dk, where omega is the frequency, central frequency, and k is the central wave number of the wave packet. So, the wave packet will consist of waves which will have frequencies centered around omega. For our case, energy equals h bar omega, which means Vg is 1 by h bar dk. So, please keep in mind, here we are trying to understand the motion of electron, how the electron actually moves in a solid or in a device when they are confined or when they are in a actual device, like they are moving in a channel, and in that case we borrow some ideas from classical wave mechanics, like the idea of a wave packet and its group velocity, the notion of the group velocity. And now we will try to see if we apply a voltage on the device or electric field on the device, which will exert a force on the electron, electric force on the electron, how this wave packet will move. So, that is what we will try to see here. And so, if we apply a force F by virtue of a applied voltage using a battery, the amount of work done by this force will be F times dx, where dx is the distance or the displacement of the electron. So, this will also be the change in energy, amount of work done will be equal to the change in energy of the electron. So, the change in energy of electron will be dE equals F times dx, and dx can be written as dx by dt into dt. So, dx by dt will be the velocity, which is the velocity of electron wave packet, the group velocity times dt. So, this dx by dt will be Vg, and in this case this expression will be F dE equals F times Vg times dt. So, this implies that dE or F will be equal to 1 by Vg dE by dt. Okay. So, this is the relationship that we obtained, and this can further be expanded as dE by dt can be written as dE by dk times dk by dt by multiplying and dividing by dk. Okay. So, now we use this relationship between the group velocity of the wave packet and the energy as we derived earlier. So, we have this relationship between the applied force and the 1 by Vg by Vt, or it can also be written as 1 by Vg dE by dk times dk by dt. So, by using this expression Vg equals 1 by h bar dE by dk, and writing dE by dk from this expression, from this expression dE by dk will be F times Vg times dt by dk. Okay. So, this is the expression for the relationship between Vg and dE by dk, and so if we differentiate this expression with respect to t, then we obtain 1 by h bar d by dt of dE by dk, and now this dE by dk can be written from this equation From using this equation, we can write dE by dk, and that will give us basically dVg by dt 1 by h bar d by dt. This dE by dk can be written as F times Vg Vg we write as dE by dk, dt and dt goes away, 1 by h bar d by dk, by writing Vg as 1 by h bar dE by dk times F. So, by using this expression, we can deduce the relationship between this dVg by dt is like acceleration in classical mechanics, the relationship between the force and the acceleration. So, this ultimately turns out to be 1 by h bar square d to E by dk square times F. Okay. So, if we equate this with, so in this case from here we can write force is equal to 1 by h bar square d to E by dk square times dVg by dt. And this first term can now be written as like a modified mass, because if we write it like a modified mass, it will be like our classical motion equation, classical equation of motion, Newtonian equation, classical mechanics equation of motion. So, in this case F, the applied force, is basically the acceleration of the electronic wave packet times a parameter which we write as m star. We do not call it the mass of the electron, it is not the mass of the electron, it is a modified mass, and this is known as the effective mass of the electron, and it is defined as the 1 by h bar square 1 by h bar square d2e by dk square by this parameter basically. And this is an important result because now in a way the quantum mechanical treatment of the electron in solid has been encapsulated in the idea of the effective mass here. And by encapsulating the quantum mechanics in the notion of effective mass, we can now use the classical equation of motion to find out the effect of an applied voltage or applied force on the electron. Okay, so that way it is quite an elegant concept because it simplifies the understanding and the calculations. So, we just need to sort of instead of using the mass of electron, we need to use effective mass of electrons, and at many places we can still use our classical concepts if we properly define the group velocity or the electronic wave packet. Okay, so, I will recommend you to read more about the notion of effective mass from especially from the text by Robert Pierre titled as Advanced Semiconductor Fundamentals. This book discusses the KP model, the EK relationship for solids, and this idea of effective mass in a very concise and very simple way, easy to understand way. And please go through this, and I will see you in the next class. Thank you for your attention.